Alright guys, can we start doing this problem sheet too? I don't know how many, did you guys have a go at these questions? I don't know. Okay, let's start with question 1. Okay, can I give you like some time to do question 1, then I will go through it, right? Can you do question 1 please? So I will just go around and if you, I don't know if you've already done question 1 or not. You need help. Just try question 1 and then I will show you how to do it. Okay. You know the Bernoulli distribution, Bernoulli, right? So the probability that x equals to k is what? What is this? The Bernoulli. Yes. Yeah, but what's the probability? What's the probability? It's p if k is 1. And it's 1 minus p. Oh yeah, k is 0. I try to do it now. You see. It's similar to the example I did today in the earlier class. Yeah, it's 1. Are you guys okay? Try and see. Yes. Yeah, this one is difficult. Skip this one. This is difficult. Try this one. Should go. Yeah. Okay, sir. You have questions?
For this one, if it starts with k0 over this k0.
Yeah. Okay. Question 3 is difficult, right? So if you've done question 1 and 2, go to question 4. Right? Question 3, this one is difficult. Don't try this one. This is a difficult one. Okay, anyway, let me show you how to do question 1, if you haven't done it already. I know most of you have. Right. So let me do question 1 first, okay? So question 1 is really not difficult at all, because I'm sure all of you know what the Bernoulli distribution is. The Bernoulli distribution takes two possible values. Is k equal to 0 or k equal to 1. K equal to 0 with probability 1 minus p, 1 with probability p, right? So what is W of f here? Would be what? Would be 1, okay? So the limit of the probability that x equal to k as k approaches 1 will be the probability that x equal to 1 divided by 1 minus f at 0, okay? Now probability x equal to 1 is p. The probability f at 0 is, what is f at 0? Will be 1 minus p, right? Because when k equal to 0 you have this probability 1 minus p. So f at 0 is the same as this probability, which is 1 minus p, right? So this is equal to 1, which is not equal to 0, right? Are you with me, guys, or no? So hence okay, all right, so this, can you do question 2, please? Question 2. Yes. You okay?
This question is well,
Yeah, that's the eta function. You don't need to worry about it. because it will cancel out. You don't need to know the properties of this function. Because when you do the calculations, it just will cancel out. Yeah, try it. I mean, this will cancel out. Yeah. Yes, okay. Can you do question 2, please, now? You done question 2? What about you guys? You done question 2? You guys okay? Take your time. Okay, sir. Yeah, you don't need to worry about it. Just this will cancel out when you do the calculations. You put it in here, this will cancel out. So you don't need to worry about it. All right. So let me show you now how to do question 2 if you haven't done it already. Okay. So this is question 2. So you have the probability that x equal to k equal to 1 if k, I'm using x also k, yeah. If k equal to k0 and 0 otherwise. So clearly in this case there's only one point, so w of f is equal to k0, right, clearly. So the limit as k approaches k0 of is equal to the probability that x equal to k0 divided by 1 minus f k0 minus 1. Right, so this is 1 divided by 1 minus. Now, what is this, guys? Tell me. What is the CDF at k0 minus 1? It will be 0 because there's nothing to sum over. Okay, so this is 1. So hence alright, can you now do question 4 please? Question 3 is difficult, but can you try question 4? You should be able to do that. Question 4. the eta function, you don't need to know the eta what the definition of eta function is. I mean the zeta function, what else? Because the zeta function, when you write down the ratio, it will cancel out. Because when you do this ratio, the eta function in question 4 will cancel out. Alright, so you don't need to know anything about the zeta function. Okay.
Sorry.
Yeah, I mean, just like I did in the first one example, you can write this as the sum of the probabilities from k plus 1 to infinity. You understand? So because x greater than k means, so I think you can I use some kind of so it should be greater than equal to, because or minus this probability is greater than. So it will be the sum of these from I to k to infinity. Okay. So right, so it will be like sum I from k to infinity was probability I minus s over the function. I know it's a little tricky. The question 4 is a little bit tricky. So if you haven't done it, let me show you how to do it. It's not all questions are straightforward. So this is question 4, right? So you have the probability that x equal to k is equal to this is the probability mass function. So clearly it's clear from the domain that w of f must be infinity. Okay? So what you need to compute is the limit as k goes to infinity of the probability that x equal to k right, like this. Okay, and this, as I said, you may remember I did the example on the Poisson distribution. You need to use that technique. Well, part of the technique I used. So this you can write as like this, yeah. Now, what is the 1 minus of this? 1 minus the probability that x is less than or equal to k minus 1 is the same as what? Yes? Okay. Are you with me, guys? Okay. This is, I mean, the same thing. I did this same thing when I did the example earlier today. Okay, and you can write the probability that x is greater than or equal to k as the sum of the probabilities x equal to I from k to infinity. Okay. Okay. Now this is where I'm going to introduce the this is where I'm going to. We know the probability x equal to k is this. Alright? Yeah? You can write like this. Now you will see that the two eta functions, the zeta functions, cancel out. Alright? This guy cancels out with this one. This is what I meant. I told you earlier that you don't need to know anything about zeta function to do this problem. Right? It's because they cancel out. So this would be the limit as k goes to infinity Alright, now the problem is how do you work out this out, right? That's the next question. So I'm going to use a trick which some of you might know from analysis that there's a trick which says that it says something like this. If you have something like the sum of g I from k to infinity, right? You can approximate this by the integral of gx dx from k to infinity. This is under certain conditions, I mean, which I'm not going to check because it will involve a lot of work, right? So you say under certain conditions, the sum of this function from k to infinity is approximately is the same asymptotically the same as the integral of g for k to infinity, right? I should say as k goes to infinity. Okay. So I'm gonna use this trick here, right? So I'm replacing the sum by an integral. So this, if you use this trick, this guy here would become the limit okay. See what I've done? I have changed the sum, right, by an integral from k to infinity, right? So this would be k. Now what's the integral of this? I'm sure all of you know. What's the integral of this? Okay, now this would be the limit as k goes to infinity of k power minus s. At infinity it would be 0. At k it would be k 1 minus s divided by 1 minus s, provided 1 minus s is less than 0, right? Okay, if 1 minus s is less than 0, then the limit at infinity will be 0. The limit at k will be this, right? So this would be the limit of s minus 1 divided by k as k goes to 0. And this will be 0. So the limit is 0. So hence, so the conclusion here is different from the hence the ETT will hold. So in this case, the limit happens to be equal to 0. So the conclusion is that the ETT will hold. So in other words, one of the three conditions that I gave you last week or the week before will be satisfied, right? Okay. Is this clear, guys, or no? Yes, you have. To
from infinity k to go from infinity to k equals to 0 evolve.
this one, you mean this one? Yeah, if x equal to infinity, sir, this will be 0, provided 1 minus s is negative. If 1 minus s is a negative number, infinity to a negative number is 0.
Yeah.
That's what I have done, sir.
Yeah.
Yeah. So we need to assume this condition, otherwise we can't do this problem. And do you have a question, sir?
No.
Is that clear to all of you or not? K to infinity, yeah. K to, it should be k to infinity, yeah. It should be not 0, infinity. Yeah, thank you. Are you guys okay with this or not? And you do the next one, please, question 5. If this is okay, and you do the next one. You guys okay? I gave, if you go to the website, I gave you a list of formulas so you can remember. It's on the website, first website, not this one. Yeah. You alright? Yeah. Okay. Let me know if you have any questions on this, guys. If you don't, please do the next question 5. I can give you a hint. To do question 5, you need to use the Lopitas Rule. I'm sure all of you know what the Lopitas Rule is. To do question 5. Yes, okay. Alright guys. How far had you got, guys, with question 5? Alright. So here you are told the probability that x equal to k is minus log base 2 of 1 minus 1 So it's obvious that w of f must be infinity, right? So we want to find the limit Are you with me, guys? We want to find the limit of this as k goes to infinity, right? So what would this be? This would be the limit of minus log base 2 of right, and in the bottom you have 1 minus the CDF, which is 1 minus log base 2 of alright guys, are you with me or not? Yes? Okay, now how do we work this out? Let's see. So k goes to infinity, of course. Now this one you can simplify. This is minus log base 2. You should take this to the numerator and simplify. You get k squared plus 2k divided by k plus 1 squared. And in the bottom, the 1 and the 1 cancel, so you have log base 2 of k plus 1 divided by k. Yes? Okay, now I'm going to use, you know that the log of a quotient is the difference of the logs. I'm sure you know that. So you can write the numerator as minus log and plus 2 log okay, and the denominator you can write it as log base 2 of k plus 1 and minus log base 2 of k. So how did I get from this to this? I just simply use the fact that the log of a quotient is the difference of the logs. I'm sure you know that. Okay. Now, to go to the next step, I think I already told you the hint I gave you is to use the Lopitas Rule, right? So do you know the property that, okay, let me write it down. If you have, let me write it, maybe here, log, if you have log 2 of, say, z, okay, and you should differentiate this with respect to z. This is the same as 1 divided by z multiplied by log of 2. So this is the property I'm going to use in a sec. Okay, so do you know this property, guys? That the derivative d by d, the derivative of log of z base 2 is equal to this, right? So if you use this property, this is what you get. You get minus plus Do you see what I've done? What have I done here? I used the Lopitas rule, which means what? I have differentiated the top and the bottom with respect to k. So if you differentiate the top with respect to k, this is what you get, and the bottom with respect to k, this is what you get, right? Alright, so a few things cancels. This guy here cancels with this, this all cancel, right? So let's see what we get. We get so this becomes equal to the limit k goes to infinity of, in the top you have minus 2k plus 2 divided by k squared plus 2k plus 1 over k plus 1. In the bottom, you can simplify the bottom to be the following. It will be minus, if you simplify the following, you get minus 1 over k plus 1. So k times k plus 1, I mean k times k plus 1. Alright, this is what you get. Correct me if I'm wrong.
Is there a
Sorry? Oh yeah, there's a 2. Yeah, you're right. Thank you, ma'am. Yeah, there should be a 2 here. I left out. Yeah, thank you. Yeah. Right, now taking this to the top, this becomes, let me put it here, and it's easier. Taking this to the top, it becomes the limit as k goes to infinity of minus cancels, k plus 1, so it's 2 k plus 1 squared divided by k plus 2 minus 2k. This is what you get, I think. Correct me if I'm wrong. And this becomes the limit as k goes to infinity of and a lot of the things will cancel, except, I know it's long calculations, I know. It's divided by 2 divided by k plus 2. Sorry, this is k plus 2, which is 0. So hence I mean, the calculations are long, but it's not that difficult. But you know, just calculations are pretty routine. It's just a matter of using the Lopitas Rule, right, and simplifying things. You get the limit to be equal to 0. Right, guys? Any questions? You ready to go home? Tired? Late in the day. All right. Question. All right. This is question 5. Okay, question 5. And question 6 is difficult, so I will cross this out, right? But question 7, you should be able to do this. So maybe when you have time, try to do question 7. You should be able to do that. Routine. Try. I mean, if you have problems doing it, just look up the solutions. Solutions for all the problems are online in the post website. You know where to find them, right? Yeah. So if you have problems doing it, just look up the post website, right? Okay. But before you look it up, just try to do it. Okay. It will help you in the exam. Okay. And also, you should now be able to do the quiz number 2. Quiz number 2 I gave you yesterday. You should be able to do that. Okay? Alright, guys. I'll see you next week, but if you have any questions before that, you know where to send me, where to come in. You know my office. And you can email me 24/7. You can Zoom me, it's 24/7. And whenever you can come and see me. Yeah.
Just you know the problem sheet 3. Have you studied the content for it?
Which one?
For problem sheet 3. Will we be able to do it?
Which one are you talking?
Problem sheet 3 for next week.
Next week, yeah.
Will you be able to start the questions or are we not?
No, not yet.
Not yet, no.
Not yet, because I haven't covered the material yet.
Oh, okay.
Yeah. Maybe, I don't know. I will let you know by Friday this week which problem sheet will be covered for next week.
Oh, okay.
Okay.
That's fine.
Okay. Yeah. Alright, guys, if you have any questions, email me or Zoom me or come and see me in my room, okay? So have a good week, guys, please. You guys okay? See you.
See ya.
If you have any questions, come and see me.
Okay, thank you.
Yeah.